results on the recovery of silicon from decommissioned solar panel, repurposing as an anode materials for lithium-ion batteries.
Nowadays, in both globally and in Vietnam, we are witnessing widespread adoption of solar panels as a green energy source. Solar panels last approximately 20 to 25 years. At the end of their life cycle, they are collected for recycling to utilize the valuable materials, especially silicon. However, for recycling silicon to reuse in new solar cells is highly complex, requiring large amounts of toxic chemicals to remove the impurities and to restore the crystal structure. Meanwhile, silicon can use as a anode material in lithium-ion batteries with specific capacity of up to 4,200 mAh per gram, which is 10 times as high as that of conventional graphite anodes. For this application, silicon does not require high crystallinity and also can even from the remaining impurities. As a result, the cost for refinement process, which is accounting of up to 70% of total cost, can significantly reduce. Drawing from this practical background, our team has chosen the research on recovery of silicon from decommissioned solar panels for repurposing as anode material in lithium-ion batteries. The main focus of this research is to exploit the potential of silicon as a high-performance anode material.
However, despite high capacity, silicon suffers from severe volume expansion, which leads to structural collapse and rapid capacity fading. To address this issue, graphene, a low-dimensional materials with superior electrical conductivity and excellent mechanical properties was introduced to enhance electrical durability. From this perspective, the project aims to address two main questions. First, can the silicon be recovered and refined from waste solar panels using a simple, low-cost, and environmentally friendly process for using as a lithium anode for lithium-ion batteries? Second, can the electrochemical performance of the silicon be effectively improved by forming a composite with graphene? To answer this question, four specific research objectives were defined. First, to develop a simple process for refining silicon recovered from decommissioned solar panels. Second, to investigate the electrochemical properties of silicon after refinement and to evaluate its feasibility in lithium-ion batteries. Third, to fabricate a composite of silicon and graphene to enhance the electrochemical performance. And finally, to assemble a prototype lithium-ion batteries from silicon, graphene anodes, and commercial LFP cathodes.
Based on the objectives, the research process of the team is as follows. First, the silicon was recovered from the end-of-life solar panels with physically separation in section 2.1, followed by refinement process using acid and alkene solutions enhanced with sodification. The silicon sample before and after refinement were evaluated and compared using NX, XRD, and SEM techniques. To improve the electrochemical properties, a silicon graphene composite was synthesized via high-energy ball mining, and electrodes and half cells were fabricated with standard process in section 2.3. The electrochemical properties were analyzed using CV when specific capacity and cycle life was evaluated using GCD.
The chemical compositions of the silicon after and before refinement was analyzed by edits. The results in figure 3.1 and 3.2 indicates that the Aluminium, which was the main impurities of raw silicon, has been effectively removed, leaving primarily silicon and oxygen. The HRD analysis shows that the silicon after refinements exhibits an amorphous structure. SEM image in figure 3.4 and 3.5 reveals that the particle morphologies of silicon remains nearly unchanged after refinement, with the particle size ranging from approximately 5 to 50 micrometers. For the composite silicon graphene materials, the SEM image show the composites have particle silicon uniformly decorated with graphene sheets, and the ellipse mappings um, represent that the 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 homogeneous distributions of silicon, carbon, and oxygen throughout the composite material. The electrochemical performance result of the material was the core finding of this study. In the in figure 3.8, the CV curves of raw silicons indicates the display distinct cathodic and anodic peaks corresponding to the reversible lithiation and dilithiation processes, demonstrating the recyclability of the materials. From the GCD results in figure 3.9, we can see we can witness that the silicon after refinement electrode have their initial capacity reached approximately 1,600 mAh per gram. However, rapid capacity fading occurs and the electrode fails after only 50 cycles. This indicates that silicon after refinements have functions as an anode for lithium-ion batteries. However, its cycle stability still remains limited.
To overcome these limitations, a silicon graphene composite was evaluated. CV measurements show similar oxidation and reduction peaks to those of silicon, and this composite has specific capacity of around 600 mAh per gram and has a stable performance over 100 cycles, demonstrating an improvement in stability compared to pure silicon. Subsequently, a fuel cell was assembled using silicon graphene anode and FFP cathode. Charging and discharging at 0.5 C shows stable performance after 50 cycles, and the battery can power common LED, highlighting its practical application potential. In summary, this research successfully achieved its objectives. First, successfully have a process to refine and recover the silicon from anodized solar panels, achieving cost saving at least 50%. Second, evaluated silicon graphene evaluated electrochemical properties of silicon after refinement. And third, a silicon graphene composite was fabricated, demonstrating an improvement in stability. And fourth, a prototype lithium-ion batteries was assembled using silicon graphene composite anode and LFP cathode, demonstrating a strong potential for practical application.
Based on this result, there are several future results that the project proposed. First, to optimization the silicon to graphene ratio in the composite system. Second, to researching on the alternative strategies to protect the materials their electrode materials, like such as the core shell materials or the polymer coat layer materials to endurance, electrode durability. And finally, to optimization their economic efficiency and their environment performance throughout the recovering and refinement and refining process.